3.2, we're going to take a look at Rolle's theorem and the mean value theorem. And I mean, it's fine that they've titled this section in this way, but Rolle's theorem is really just a special case for the mean value theorem. It's a case that's easier to work with. So we start this section talking about Rolle's theorem because it's easier than just starting to talk about the mean value theorem from the get-go. So here's Rolle's theorem. Rolle's theorem says, suppose that you have a continuous function on the interval, closed interval AB, and it's differentiable on the open interval AB, and the endpoint for A and the endpoint for B are at the same height. Okay, so the picture you have in mind maybe looks something like, I can get it drawn very well, this. Okay, it's smooth, it's continuous, and the height at the far left point A and the height at the far right point B are the same. Okay, I'll put a coordinate grid on here just to give some perspective. This is the height we're talking about. F of A equals F of B. Okay, that's not drawn well. Okay, so that's the setup. If it doesn't have this setup at the beginning, you can't use this theorem. We've seen this happen before where I said check the conditions to make sure something works. Do you remember doing that? Something called the intermediate value theorem. And if the intermediate value theorem conditions at the beginning didn't work, then nothing else is going to actually be true after that, or at least not necessarily true. So these are the conditions. Smooth, continuous, endpoints match. Then, if that happens, there will be a location somewhere in between A and B where we have a derivative of 0. And we've talked about the fact that derivatives of 0 look like flattening out spots. Hang on, this isn't working. So this is a horizontal tangent line, right? Horizontal tangent line has a slope of 0. And these horizontal tangent lines are only going to occur when I have places on my graph that flatten out. Some of those places that we talked about last time are relative extrema. This is one of those. This is a relative maximum point. It's a place where I have a change from increasing to decreasing. Right? So it's a relative maximum point. And I could have, or a peak, I could have a valley and it would work as well. Right? If I had a relative minimum point, that would be okay. There's one more value that we could have. We didn't really talk about it too much last time. But if the graph did something like this, where it flattens out in the middle, right? Do you see how it's flattening out right here through the middle? That would be another place where you'd have a derivative of 0. And that doesn't fit with my picture because I need my endpoints to match. But I just want you to recognize that's another possible way that you could actually have a flattening out place. So this theorem says between two of these values that have the same y value, there's going to be a place where I have a horizontal tangent line. I have a derivative of 0. It's going to happen. It's guaranteed to happen. So on our first example, what we're asked to do is to simply determine whether the Rolle's theorem can be applied. That's step 1. That's a 3-step process, okay? I feel like I'm doing the intermediate value theorem with you again. 3 steps. The first thing you have to do is you have to verify that it's continuous. The second thing you have to do is to verify that it's differentiable. And then the third thing that you have to do is to verify that the endpoints match. Right? Those are the conditions. So the part that's highlighted in red, this is how we do it. All of these are that step that's red. And then it says, if it can be applied, then find the values where the derivative equals 0. So it means take the derivative, set it equal to 0, solve. So that's one step. So if this red part works out, we're going to follow through with the green part. If the red part doesn't work out, I mean, we fail. It fails to be continuous in one of these. What fails to be continuous or differentiable, or the endpoints don't match. Then we do the part at the bottom where it says, explain why we can't use this. Explain exactly the place where it failed. Okay? So, to start with, here is our function. We need to verify that it's continuous. Is negative x squared plus 3x continuous? Yeah, it definitely is. Do you remember why? I think it was you. Because what? There's no denominator. Instead of saying it from a negative perspective, can somebody say it from a positive perspective, like why it is instead of why it isn't? It's a quadratic. Okay, so it's a polynomial more generally. So the fact is that this happens automatically because it's a polynomial. And we actually had a theorem that said polynomials are continuous. Yay! So that's a great theorem because then we can always just say it. We don't have to like prove anything. It's just a given. Differentiable. The reality is that the reason's the same. Polynomials are wonderful. They do everything we want them to do. They're continuous, they're differentiable. They're just such nicely behaved functions. And the reality is it simply is because it's a polynomial. And polynomials are differentiable. And their polynomials are differentiable and continuous on all real numbers. So the fact is we do have an interval here, and it's going to matter here in a minute, but it doesn't matter for parts A and B on this, or for parts 1 and 2 here that I've described. It doesn't make any difference. Now, let's say, for instance, Jeffrey, you mentioned not having a denominator, and it doesn't have a denominator, and you're absolutely right. But let's say we had a function that did have a denominator. As long as that interval is not causing a problem with the denominator, it could still work. So if we're dealing with a rational function, ones that have denominators, or maybe even a radical one, right, ones with square roots, the answer is not always no, just because it's one of those. We have to be more specific and careful because of the interval we're working with. But the beautiful thing about polynomials is we don't care about the interval. It doesn't matter. Okay, so we're 2 for 3 at this point. Step 3 now. Step 3 says that we need to decide if the endpoints values match. So in particular, what I need to check what f of 0 is because it's the left-hand endpoint. And I need to check what f of 3 is because it's the right-hand endpoint. And I need to see if for sure that they match. Right? Now, when I did the intermediate value theorem, I did this too. But my goal when I was doing the intermediate value theorem was that they didn't match. I need them to not be the same thing in order for the intermediate value theorem to work. For Rolle's theorem to work, I need them to be the same thing. So let's check out what happens when I plug in the number 0 into this function. Somebody say it real quick so we can move on.
0.
It's 0. Thank you very much. All right, and then the other one, 3, which requires more work, obviously, because it's 3. What does it give me? It actually gives me 0 as well. So this works out, right? So this actually verifies the third part of the reason. So as you're doing this, just like when we did the intermediate value theorem, I'm going to move this so I've got some more space to work. You need to say what this means. All of that means, right? All of these details mean that Rolle's theorem, what's the language they use, applies. You have to state it. Rolle's theorem applies, Rolle's theorem does not apply. Right, this is like when I ask my kids a question, and instead of saying yes or no, they start giving me excuses right away. I didn't ask for excuses, I said yes or no, right? You got to say the yes or the no. And then you can do either the green or the yellow parts that I highlighted, depending on which one it is. So on this one, since Rolle's theorem applies, it's the green highlighted part that I'm going to do. The green highlighted part says, if Rolle's theorem applies, take the derivative, set it equal to 0, and solve. So that's what we're going to do. So our function, negative x squared plus 3x, what's the derivative of negative x squared plus 3x? Negative 2x plus 3. Beautiful stuff, right? And then we're going to set it equal to 0, and we're going to solve it. So negative 2x equals negative 3. X is 3/2. Everybody good on that? You might end up getting more than one answer here. We've had that happen in the last section, right? We had it happen in the intermediate value theorem section. What you want to check, though, is that one of the answers should always, has to always, if you've done all the work right, must always be on the interval that you were working with. Because Rolle's theorem said it did, right? And it's a proved theorem. The proof's in your book if you want to go take a look at it, okay? Has to absolutely be in between the interval. And it is, right? 3/2, it's 1.5. Happens to be exactly halfway between 0 and 3. That doesn't always happen. But it actually is between the two values. So if you take a look then on this one, the C value that it's referencing right here is exactly the 3/2. If in fact you got 2 or more x values and both of them are on the interval, you need to identify which one it actually found that is. All right, so let's say for at the end here, this x value, you got 3/2 and you got 5/2. 3/2 is in the interval, so 3/2 is the answer to the question. So C is equal to 3/2. You wouldn't say C is equal to 3/2 and 5/2. Does that make sense? 5/2 is in my interval too. I gave another example that was. I wanted one that wasn't. I was doing that too quickly. How about 7/2? Will that work? Yeah, that one won't work. Okay, so if you've got 3/2 and 7/2, you'd need to identify which, if there's more than one, doesn't work and does work. Okay? Any questions on that? Okay, another example. Same directions, exactly the same. So on this one, I have x to the 2/3 minus 1, and my interval is -8 to 8. You may not know what this graph looks like, and that's okay. If you wanted to get a perspective of it from a visual, like if you wanted to graph it just to see so that you'd have an image in your mind, you could do that. I suspect on this last one I didn't say it, but you probably had a pretty quick image of what this probably looks like. It's parabola, it's opening downward. It actually looks a lot like this picture I drew over here, right? So this one is not a parabola opening downward, it's something else. So if a visual will help you, that would be great. It doesn't prove things, by the way, but it would be something that would give you a perspective. We need to check to see if things are continuous, differentiable, and if the endpoints match. And the reality is that we'll test all three of them, and if something fails, then we have to identify every piece that fails. So that's why we're going to test all three anyway, so hopefully by now you're already catching the fact that this is going to fail, because I'm leading you down that path, right? My language is doing that. Leading questions are terrible. Yes, slap my hand today. Okay, continuous, that's our first one. Is it continuous? So is this function continuous? Well, if you weren't sure, and this was an unfamiliar enough piece, you could look at a graph to verify it. Like that would be a possibility. Because if on the graph you saw an asymptote, you'd immediately know it's not, right? Sure. Another thing that might help to decide if you were sure, a little unsure, is to remember what x to the 2/3 means. Well, it means the cube root of x squared. Okay, so continuity issues are always issues of I am not allowed to let x be something. Right? I mean, that's what a continuity issue is. Is there anything that you're not allowed to let x be if x is squared and then you take the cube root? 0 is okay. Actually, 0 is a good question. We can have zeros underneath the denominator, or underneath radicals. That's okay. Negative, that would be a good way to check too. So let me check the 0 with you, and then let me check the negative with you. So if we did 0, what's 0 squared? 0. What's the cube root of 0? It's actually 0. So 0 works, but it's definitely a thing that we would want to consider. Negatives are another thing that we want to consider anytime we have radicals. So if I have a negative, just pick one, because the type of one's not going to make any difference. Negative 1's a great number. How about negative 1 squared is 1. What's the cube root of 1? 1. So negative numbers work as well. The sign's not going to matter. If I had a square root and I didn't have the x squared underneath there, Jared, we would definitely have some problems with negatives.
Yeah, I didn't notice the square.
Oh, it's okay. No worries. Okay, so positives work, negatives work, zeros work. This one's good to go. And if you look at the graph, it's going to look good to go too. It looks funny. It's a funny looking graph, but it doesn't have any breaks in the graph and there's no asymptotes present. So this one's good to go. And the reason it's continuous is because it's a root. In particular, a cube root. Cube roots, they're nice. Square roots, not so nice, for exactly the reason that Jared was sort of mentioning with the negatives, right? But cube roots are good. So this is because it's a cube root, not roots, cube root function. I'll put a function at the end. So we're good to go. It's continuous. The second thing to test is that it's differentiable. Differentiable means I can find the derivative and it exists everywhere. So this is probably one of those places where it would be a good idea to look at a graph. So if you have a calculator and you haven't done it already, go ahead and put in x to the 2/3 minus 1. Yeah, this is with the picture I almost drew, but then I want to make sure I looked at it and remembered it right, so I don't have it in my notes. Okay, so what does it look like? A seagull. Very good description. Do you guys see the seagull? I like that. Yeah, it does kind of look like a seagull. So it looks something like this. It's a little exaggerated that I've made it to sort of make it bigger, but does yours look like that? No? Let me see yours, Siobhan.
I let someone from business calc on my calculator, and I think they changed something.
It's okay, we can turn that off. And then let's just do zoom 6 for a standard window. I think it'll work now. Anybody else's graph not showing up right? It's all good. Okay, the question is this differentiable everywhere? So, there were some locations, Jared's saying no, that cause problems with differentiability. So what are you noticing, Jared? There's a cusp, right? There's a sharp turn right there along the y-axis, yeah? And that's a point of things where it's going to be not differentiable. And if you remember, the reason for that is because if we were to draw tangent lines, right, we'd have these great tangent lines going on, but then eventually we'd have this sharp turn where right at that cusp, what do? Because on the left-hand side, I had these tangent lines that were, negative slopes, and on the right-hand side, I immediately have these tangent lines that are positive slopes. There's no smooth way to actually make that work. So this is actually not differentiable. And it specifically is at x equal to 0, or you could say along the y-axis, that would be fine as well. That is not differentiable at x equal to 0. That's like a big red flag. It's an x. Rolle's theorem is not going to work for this function. It doesn't mean that the results of Rolle's theorem, like the statement, might not be true. It could be, depending on what your function you were working with, but it's not guaranteed to be true. So since the conditions of Rolle's theorem are not met, we're actually not going to be able to do what I highlighted over here in green, right? I'm not going to be able to set it equal to 0 and solve it for sure. So let's take a look at part 3, just so that we've got all the pieces of why it may or may not be differentiable, or why it may or may not apply to Rolle's theorem where it fails. We're going to test the endpoints just for good measure, for being thorough. And also because if in fact you had gotten the first 2 to work, I want you to see that this third step still might not. So we're going to test -8, and we're going to test 8. So if I put in -8, I'm going to write it with the cube root notation because I think it's easier to work with. And then what was the number at the end? -1. Okay, so what is -8 squared? 64. What's the cube root of 64? 4. And then 4 minus 1 is 3. And then what do you notice happens when I do the +8? Yeah, it's the same thing. That negative actually ends up not mattering because I've squared the x in each part, so I still end up with 3. So this actually would check out if I needed to check this particular step. So the conclusion to the problem is the yellow part over here that was highlighted. If Rolle's theorem cannot be applied, explain why not. So we're going to say it. Rolle's theorem does not apply. Because f of x is not differentiable at x equals 0. And let me make one more comment about the fact that the x equals 0 is there. It's not just that it's not differentiable at x equals 0, it's that 0 is on the interval 8 to -8, -8 to 8. Right? If this interval went from 1 to 10, it'd be differentiable, no problem. There would be no cusp in that interval. It's because the interval that we looked at from -8 to 8 had the differentiability problem. Does that make sense? Okay.
But if we were to do like the saying the continuous of like the graph, and we were to do like the jumps included,
Yeah.
would we include 0 to 0, or would it just be -infinity to 0 and then jump from 0 to infinity?
Well, Rolle's theorem has to be continuous on a closed interval and an open interval,
Right,
so there's
like,
no
like,
jumps.
Like, this is like kind of just like unrelated to this, but I'm just trying to figure like would that be included in that? Like just as
No. If you were talking about, like, if the question said something about differentiability and it wasn't in an interval that was included in your description, then you could still be differentiable on a series of other intervals, and it would be okay.
Okay.
I think that's what you're asking. Does that sound right? Okay. One more question, same directions, trig function. Steps continuous, differentiable, and endpoints. All right, the function is sine of x. Is the sine of x a differentiable? Is it a continuous function first? It's continuous. Because why? Yeah. Because it's sine, that sounds sort of like, like saying, why are you tall? Because you're tall. But it is, it's because f of x equals sine x. I mean, that's it. We actually had a theorem, just like the polynomial theorem, which was more broad, that said sine functions are continuous. And the differentiability works the same way. Because it's a sine function, and cosine would work the same way. Sine function, cosine functions, not all trig functions, just those two. Are smooth and continuous and differentiable. They're all the good stuff, just like polynomials. We want to check the endpoints, though. So our endpoints here are at 0 and at 2 pi. So what is sine of 0? It's 0. And what is sine of 2 pi? It's also 0. So these match, right? They do. So the result of those 3 steps is that Rolle's theorem applies. So then, since Rolle's theorem applies, what am I allowed to do? Well, I'm allowed to take the derivative, set it equal to 0, and solve. So here's my derivative for sine. What is it? It's cosine. Where does cosine of x equal 0? At pi over 2 and 3 pi over 2. And a lot of other places too as well, right, Anthony? Yeah. This is just a couple of the locations. It's actually the only locations I care about. Why? Because it's the only ones that are in my interval from 0 to 2 pi. So this actually has a lot of other answers, but I've actually only listed the answers that I care about at this point anyway. There are 2 locations on this one that have a derivative of 0. And if you think about the graph of sine, of course, this does make sense. This is my graph of sine, roughly. And this is at 0, and this is at 2 pi over here, where I've ended it. So maybe I'll just stop it right there so you can see it more clearly. And so there, in fact, are 2 locations where I have slopes of 0, right? Does that make sense? All right, so let's generalize Rolle's theorem to a broader case. This is called the mean value theorem. The mean value theorem takes Rolle's theorem, right? And what it does is it puts it on an angle. And I'll draw you a picture in a moment, but here's actually what it says. It says, suppose that f is continuous on the interval AB and differentiable on the interval AB. Those are the same conditions we have before. But there is no condition about the endpoints needing to match. So as long as it's continuous and differentiable, then there exists a number c between a and b such that f prime of c is equal to f of b minus f of a over b minus a. So here's A, here's B, and let me draw it a little bit more curved. Smooth, continuous, differentiable, it's got the 2 conditions, right? It doesn't have Rolle's theorem apply because f of A and f of B are not the same thing. Agreed? What this is saying right here at the end is that this is the slope of the line connecting A and B. I know that's abbreviated, but if I threw in here a line connecting A and B, it would have a slope. Agreed? Yep, it has a slope, I mean guaranteed, and it's not 0 because A and B are not the same. That's what happened in Rolle's theorem. And so there's going to be some location in between on the graph that has that same slope. And visually it looks like it's about here. So can you imagine taking my other picture and just tilting it? That's what we've got here. We've got the same picture, we've got it tilted one way or the other. That's all it is. And so the reason that this is just a specific case of Rolle's theorem is because if I tilt it back and I find the actual line segment that connects A and B when they're on the same y value, what's the slope of a horizontal line? It's 0. And if I were to actually put in the 0 here, right, f of c, f prime of c equals 0, that's the result in Raleigh's theorem. It said it. That's how it said it. So this is just a more broad case of Raleigh's theorem, or you can say that Raleigh's theorem is a special case of the mean value theorem. The cool thing is that on the examples for these, when it says to determine whether the mean value theorem applies, that's easier than it was for Raleigh's theorem because there's only 2 conditions instead of 3. The only conditions you have to check is that it's continuous and it's differentiable. You don't have to worry about the endpoints. Now there's more to be done after that, but those 2 pieces are easier. Continuous, differentiable. What can you tell me about the graph of f of x equals x squared? Is it continuous? Yes. Is it differentiable? Yes. And why? Because it's a polynomial. And so because of that, the mean value theorem, which we'll abbreviate MVT, like most valuable player, right? But not. Okay. So MVT applies. The part that you get that you didn't have to do before is that you have to calculate this slope. Okay? So before I checked the f of b and f of a and that they were equal. Now I'm pretty sure they're not going to be, but I actually have to still calculate them to calculate the slope. So the slope is going to be based on the endpoints I'm given here. So it's going to be f of, and it doesn't matter the order, I'll just do them in the order that are given, -2 minus f of 1 over -2 minus 1. So I do have to calculate them, so let's actually do that up here. F of -2 and f of -1. Well, it's a very simple function, right? A clean one for sure. It's not 1, -1 is just 1. Okay, so what's -2 squared? 4. And what is 1 squared? 1. So this right here is a 4 minus 1, right? Over -3. So what is the slope going to be? It is -1. Okay? That I didn't have to do before because the slopes were 0. Why did I need to do that? Well, because the actual second part of this theorem says that the derivative right here, right, has to equal that value. In this case, -1. So I need to find the derivative, and instead of setting it equal to 0, I will set it equal to the slope I just found, -1. So what is the derivative of x squared? 2x. And again, I set it equal to the slope. Make sure and write that down for yourself, because if you look back this later, you're like, why did I not set it equal to 0? Because I'm using the mean value theorem, so why? It's the slope. And if I solve this, what x value do I get? -1/2. Is -1/2 between -2 and 1? Yep. You might get answers that aren't and are, but there's at least going to be one that's between. And that's the c value that you want. -1/2. All right, last problem. We're going to fly through it. All right, we check for continuous and we check for differentiable. The interval is from -1 to 4. Jeffrey, this is a denominator, doesn't it? There is a problem with this denominator. This denominator does, in fact, create a problem. Where does this denominator create a problem?
0.
At 0. Is 0 on my interval?
Yes.
Yeah, it is. So this is like one of those places where you're like, oh man, I'm really glad I checked the conditions before I did all the work. Because since 0 is on the interval, is this interval going to be continuous? No, I should say the function. The function is not going to be continuous on the interval. Because what's actually happening at 0 on this particular function? Yeah, there's an asymptote on this one, actually, yeah. So there's an asymptote at x equals 0. And that 0 is actually between the -1 and 4, right? I mean, like, that's the problem, is that it's on the interval. And we actually had a theorem back in the day that said that if it's not continuous, it's not differentiable either. So it fails to be differentiable actually because it's not continuous. So the mean value theorem does not apply. If we had a different interval, like let's say that the interval didn't go from -1 to 4 and it just went from 1 to 4, we'd be fine. And we would say that. We would say it's continuous on the interval 1 to 4. It's differentiable on the interval 1 to 4 because the only place where it fails to be continuous and differentiable here is 0, and 0 is not on the interval. Does that make sense for everybody? So please, please, please do not fail to check those conditions, because if those conditions are not met, your problem became a whole heck of a lot easier. All right? All right. Have a great weekend. I'll see you all on Monday.